Good morning, everyone. So welcome back to QX01, Introduction to Quantum Information and Associated Technologies. So let's have a look at the program. So that's today. So today is lecture 8. So we will finish what we started on quantum gates. And then we will start on quantum algorithm. So last time, 3 weeks ago, we had part 1 of quantum cryptography, which is not yet available, but will be soon, so done by colleagues from University of Bristol. And at some point, there will be a part 2 from the company QX, which is also based in Bristol, on quantum cryptography. And then some other topics that will be touched upon, although so far, as there will be different people giving lectures, so all this schedule is not yet finalized, especially the times and the dates. But whatever happens, so next week there will be a lecture at 10 a.m. in the morning. It might not be given by my colleagues from INRIA, but there will be a lecture 9. Right. So let's have a look at the program for today and probably for next time, because I won't have the time to finish everything. So quantum algorithm, of course, I will have to talk about classical algorithm first. And then I will talk about the different families of quantum algorithm, and we'll see that there aren't that many of them. I will have a focus on what we could call hybrid algorithm, which is hybrid in the sense that it's classical in quantum algorithm. And I'll give an example of an experimental example of what was done. And then 2 examples of quantum algorithms. We can't do too many. The first one will be originally the first one, which is the Deutsche Algorithm. So that I will do that. And hopefully, my colleague from INRIA, so INRIA is the French research agency for applied mathematics and computer science. And he will talk about the so-called Simon's algorithm, which led to one of the most important ones, the Shor's algorithm, which we probably won't have time to cover because it takes few lectures to cover properly the entire Shor's algorithm. Before that, we have to finish off lecture 6 on quantum gates, and in particular, what I call practical cases. So there were 2 practical cases that I just briefly described that we will go through today. So what I mean by practical cases is the use of gates, quantum gates, and a quantum circuit for a specific function. So this can already be seen as quantum algorithms, in fact. So the first example is to create a Bell state. So say I want to create the following Bell states, so the psi plus Bell state, which is one of the 4 Bell states, if you remember. So it's a 2-qubit state, which is 1 over square root of 2, 0, 0 plus 1, 1. And so this circuit is actually the circuit I need to create this Bell state. So what we have here, if you remember from last time, we have 1 qubit gate, Hadamard gate on qubit 0, Q0, and a Synod Gate, which is a 2-qubit gate on both of them, Q0 and Q1. And at the end, I'm going to show you that we end up with the Bell state phi plus. So let's do that. So first of all, there are different steps. So it's a quantum circuit. So that means we go from left to right, and we follow what happens. So the first thing that happens is to qubit Q0, and then with the Hadamard gate, and then there will be a Synod between the 2. So the first step to do, as you can see, is to initialize the qubits. So first step, initialize. So for that, we have Q0 and Q1, and we will initialize them to being 0, 0, which I can rewrite 0, 0 if I want to. That's step 1, initialization. Step 2 is an Hadamard gate on qubit, the first qubit, so qubit Q0. So that means that Q0, so sorry, Hadamard gate, let's write it. So Hadamard gate. So I remind you, the Hadamard gate can be seen as the superposition gate. So Hadamard gate on Q0, which is 0, will give us a superposition state, 0 plus 1. So 1 over square root of 0 plus 1, right? So that means now the 2 qubit state that I started with, so the Q0, Q1, so this one, is now transformed. So Q0, Q1, which was originally 0, 0, is now transformed into but never mind, there's a parenthesis missing. So 0, 0 plus 1, 0, right? So we're getting there, but not quite. We still need to go forward in order to get 0, 0 plus 1, 1. One quick manipulation here to be aware is that, so remember that the 2 qubits, so qubit Q0 and qubit Q1, have to be handled with tensor products. But likewise, gates can be handled with tensor products as well. So that means that this operation, just this simple operation of doing the Hadamard gate on the first qubit, so to go from this state to this state, can be seen as either what I did here, sort of a 1 qubit manipulation at a time, but it can also be seen as a 2 qubit manipulation at once. So in this case, I define a operator K, which would be the tensor product between the operator H, Hadamard, the Hadamard gate, and the identity operator on the second one, the second qubit, which we haven't touched. If you look at this circuit, oops, sorry. Here we go. We haven't touched so far. Here we are at this stage here. We haven't touched qubit Q1. Sorry. So this is a tensor product for matrices. So if I write the matrix for the Hadamard gate, I've got this matrix and tensor product with identity, which would give us this. So I can apply the same rules as we saw before, as a matrix, a tensor product between this one and this one. So it would look like so, where I have 1, and then 1, 0, 0, 1, 1, 1, 0, 0, 1, and then 1, 1, 0, 0, 1, and then minus 1, 1, 0, 0, 1. So this gives me now a 4x4 matrix, which with I can handle my 2 qubits in one go, and that would be 1 square root of 2, and then 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, and minus 1, 0, 0, minus 1. Okay? So now I can apply this matrix to the original 2-qubit state. So this 2-qubit state, it's a tensor product of qubit Q0 and qubit Q1 in a 2-qubit notation would be given by 1, 0, 0, 0. In the basis, if you remember, in the basis of the 2-qubit, which is 0, 0, 0, 1, 1, 0, and 1, 1. In this case, I started with 0, 0. So the four-term column vector, the four-term ket in this case, would be just 1, 0, 0, 0, because I have the 0, 0 start for initialization. So that means I have to apply this matrix to this vector, this four-dimensional vector. And you can see, so if I do that, so here is the result. If I do that, then if I can do it here. So this times this gives me 1. And this times this gives me 1. This times this gives me 0. This times this gives me 0. Oh, no, there has to be a mistake somewhere. Sorry, this times this gives me 1. This one and this one. Voilà. And this times this gives me 0. And I end up with, indeed, and a square root of 2, of course. I have to remember that. So I end up with 1 square root of 2. And then I've got 0, 0 plus 1, 0. Which is the state that I was looking for. So this one, at this stage. So, okay, so now we are located in here, in the circuit. So we've done the Adama gate, and now we are at this stage. Now the next step is to do a Synod Gate on this 2-qubit state that we have. So, okay, so let's do a Synod Gate. So Synod applied to this vector, or this four-dimensional vector. And I've got here the representation of the Synod Gate. Remember, it's a 2-qubit gate where you basically swap the target for a given control. So if we do that, so we apply the Synod Gate to this vector. So let's do it. So this times this gives us 1. This times this gives us 0. This times this, this times this gives us 0. And this times this gives us 1. Okay? So at the end, we end up with the state that we wanted. So 0, 0 plus 1, 1, which is the Bell state that we wanted to end up with from the beginning. Okay. So we see here how we go from a quantum circuit with quantum gates. So through the entire calculation. So this is the entire calculation. But of course, the idea is not to have to do that all the time, but to play with the rules of the gates and the various 1-qubit, 2-qubit gates along a quantum circuit. And nowadays, we have several actually software that have been developed either by companies or by universities that can actually handle these circuits representation where behind at the back, the calculations are of this type. So you don't have to do all this calculation by hand, hopefully, luckily, and can just use the combination of the various gates on this software. So there will be, hopefully, there will be an example by the company Atos, when they develop their own software, quantum circuit software. And all you do at the end is just handling this kind of quantum circuits. And behind at the back, the computer will compute all these matrix multiplications and tensor products and so on. Right. So that was the first practical case. It was a sort of simple practical case. Before going to the second practical case, I just want to come back to what I mentioned some time ago, which is the creation of entanglement. Because so typically, this state here is an entangled state, so it's one of the Bell states. And what I brought here is a commercial system that can actually experimentally create this state using polarization, polarization state of photons. Okay, so let me go back to that. And in fact, in the second practical case I'm going to talk about, which is quantum teleportation, you will see that the source of entangled photon is exactly the same kind of source that I talked about, so in here, that I talked about some time ago. All right. So, right, so remember the process I mentioned some time ago on the so-called spontaneous parametric down conversion. So just a quick recap on what we said. So we have a laser. So usually it's a UV laser or near UV laser. And we send it through a nonlinear crystal, which is a piece of glass but has nonlinear properties. And we can, by doing this, by nonlinear optics, we can generate infrared photons with exactly half the energy or twice the wavelength of the incoming photon. So one blue photon basically split itself into two so-called twin photons or generated pair of photons with half the energy, because there's energy conservation, and with also some sort of geometrical properties. So in this case, they come out in cones, okay? And if you remember, I explained one cone is H-polarized photons, the other one is V-polarized photons. And if we go at the intersection of these two, we end up with this entangled state, which was HV or plus minus VH. So in this case, so what I'm about to show you is the same principle, slightly different. So we have the laser, we have the nonlinear crystal, but in fact, we have two of them. And they are what we called type 1. So I'll come back to that. Type 1. And then we have, again, our pairs of photons coming out. So here we have a photon at 400 nanometers or so. And here we have photons at 800 nanometers. So two of them. So twice the wavelength, but it's half the energy. And then we will send that onto detectors, so through optical fibers, into a box. Okay. And then on this box, we're going to see a green line. So this box, we're going to see a green line, which is going to give us what we call the coincidence rate, or basically the double measurement, double click of the twin photons that have been created. So this number will tell us how many pairs we register created by this so-called spontaneous parametric down conversion process. In this particular case, we have two nonlinear crystals as opposed to what I presented the other day. And each of them can generate identical photons with identical polarization as opposed to what I showed you the other day. Meaning that when you rotate them, so one will generate, say, two vertical photons. So let's put it in. So this one will generate photon 1 and photon 2 with vertical polarization. And the other one, if we rotate it by 90 degrees, it will generate the same thing, but rotated by 90 degrees will give us H1 and H2. So that at the end, this entangled state, and because we have quantum superposition of creation of these two pairs, of these two possibilities, of these two photons, then the state that we have is precisely the one that we just talked about. It's the psi plus, which is going to be HH, so 1 square root of 2 HH plus VV, which is the equivalent, well, which it is exactly the state that we just generated with our quantum circuit. So in a way, by doing this, we created the quantum circuit. There's an Hadamard and Synod Gate all at once, and gave us this entangled psi plus state. Okay. There are various elements in that box I'm going to talk about, but let's not worry about this. Let's just keep that in mind. And what I'm going to do is that in front of these two detectors that pick up the photons and then send them to the box, they are not detectors, they are lenses to pick up the photons, and then they go onto the detectors inside the box. So in front of these lenses, I will put two polarizers, so one here and one here, and I will rotate these polarizers, and I will show you that when the polarizers look at the same polarization, say HH, oops, there should be a 2 here. So that's photon, say 1, photon 2. Then I will see HH. When I will turn the two polarizers in the same way by 90 degrees, I should get VV. But then when I will turn the two polarizers at 90 degrees, so one will look at H polarization and the other one will look at V polarization, then I should get no coincidental events because I do not create HV photons, I create either HH or VV. Right? So let's do that. So just to be aware, so this setup that I'm about to show you, so this one, is actually a commercial setup. So now you can buy your own. So for obvious reasons, I do not give the name of the company, but if you're interested, do not hesitate to contact. I can put you in contact with them. I have no specific interest in that company, just saying. But this is nice because, well, you can see the experiment is rather small. Well, for you, it might look big, but it's actually for us who try to do the same in the lab, it's rather small. And it's quite convenient to show this process. So this, as opposed to what I showed you before, what you're about to see is a real quantum experiment in the sense that we have pairs of photons created, and we have entangled pairs of photons created through this demonstration. Now, I'm going to start first by putting the controller on. And I will describe the elements that we have here. I will turn the controller so that you can see the line I was talking about. So here, what I'm doing right now, I'm setting up the current that goes to the pumping laser, so the blue laser. So I'm setting up the current, here we go. So now it's set. Now the laser is on. So let's have a look at this. Perfect. I'm going to remove this and remove this. Voilà. Right, so now let's turn and explain what we see. All right. Okay, so what you see here, hopefully, is a green line that doesn't move. And I tell you that this green line, for the moment, well, gives us a number. I'll come back to that, which is the number, as I said, of coincidental events, so of twin photons, entangled photons, measured by the setup. So now, what is this setup? So inside that white box, there is a laser, so a blue laser inside the box. So that's just the current I set just a minute ago. And inside that box, there is these two nonlinear crystals that have been put together at 90 degrees, each of them generating either HH or VV. These photons come out, so these twin photons, now red infrared photons, so we can't see them, and even if they were, because it's infrared, but even if they were to be invisible, we would not see them because there are very few of them, so we cannot see them. But they are there. So they come out, and then you have two mirrors, each of them, so they come out in this cone, like this cone shape, as we said. And they are spatially separated by some degrees, so that means that this mirror can pick up the first one, and this mirror can pick up the second one. And each of them will send the photons through these elements. So these two elements are identical, and they are what we call collimators. So it's basically an optical lens that will just pick up the photon, send it into these two optical fibers. These optical fibers are plugged in to the controller. And inside the controller, there are single photon detectors, so sensitive enough to measure single photons and register the arrival of the photons. So, and in front of it, like I said, we have two polarizers. So these are the two polarizers. And right now, these two polarizers are both measuring vertical polarization. So if they're both measuring vertical polarizations, that means both photons can go through these polarizers, through the fibers, and be detected. And what I see right now is a value. So here you see this, you see this light, this green line. So it seems to be very noisy, but it's simply because we are at a certain number of photons. I can't really see the number, but say 5,000 events per second. And now the idea is that if I rotate one of these polarizers by 90 degrees, this value should fall down to 0 or near 0, because there's always some noise associated to it. But these values should come down to 0 because we are not looking at HV states. We are not producing HV states. We are producing HH or VV. Either two are horizontal or two are vertical. So let's do that. So hopefully this is going to work. It's not working. Let me see. Of course, it has to. Oh, yeah, here we go. It is. So it did work. So let's do it again. It's because there's some time to register. So now I put it at 90 degrees. Sorry, that's 90 degrees. And you can see, well, it's much better. So you can see the green line. So here the green line is flat. Then there is a bump because I made the first try. Then it goes up again, and then it goes down. And now it's down. Okay, so now the value is in fact 0. So I've got no coincidental events because I'm looking at HV polarizations, so orthogonal states, where what I'm actually producing is this or this, not this. So if I look at this, then I have no coincidental event, then I have 0, the double detection of this state. Now, what I can do is put the second one at also 90 degrees, And now that means that we look at horizontal states. So I should be getting back the number of coincidences, and the green curve should go back again. Go back up again. And hopefully that's the case. Voilà, it goes back up again. Not quite at the same level, because there's probably some alignment issues during the travel, but it's going up again. Okay. And okay, so what I've done is I started with this. So I had a number of coincidences. I did this. I went down to 0. Then I did this. So I went back up to have the horizontal state. And now what I can do is, which one I haven't done? This one, and which is the other sort of cross-correlated polarization measurement, and I should go back to 0. So that means if I don't get it wrong, so this one went down, so I can bring this one back up, and the number of coincidences goes down again to 0. Okay. And again, so this is a true experiment in the sense that there are true pairs of photons that are created, entangled photons, going through these lenses, fibers, and into the detectors. Just a quick word as well is that inside these collectors, inside these collimators, to pick up the photons, they're also very sharp filters, optical filters, in order to make sure that we're only looking at photons created at 800 nanometers or so. And this is very important because actually in the room right now where I'm sitting, where I'm being, there are photons at 800 nanometers that could produce some noise. But as the filter is quite narrow, plus we're looking at coincidences, only coincidences from twin photons produced by the crystal can be seen and measured. Okay. Just a quick word. What I just showed you here by doing these cross-correlation measurements is not enough to show entanglement. All right? What I showed you here is actually that the twin photons are correlated. I have not shown you that they are entangled. For that, you need to make more measurements in different bases. So in this case, I would probably have to make more measurements using plus minus 45-degree angles, or circular right, circular left polarization basis, okay? I don't have time to do this, but trust me, we did it. So this does produce entangled pairs, and what we saw here is a first observation of that. All right, so now we can switch this thing off. All right, here we go. Okay. All right, so I promised that, and I wanted to show you this. And once again, this is a commercial system. So it's for educational systems, so it's quite nice. And it's easier to create this state using this process than the one I showed you last time. The only reason why we should carry on working with the other system, so this one, this one, is the fact that using this setup with only one crystal but orthogonal polarized photons produced is because we can produce directly the psi minus state, which is the sort of called the singlet state, or the Bell state, which remain the same whatever basis you choose. So for practical purposes, say quantum cryptography, for instance, this state is very interesting. But nevertheless, this is also an entangled state, and they're all entangled states. Right, so let's go back to the practical cases. So practical case number 2. So it's about quantum teleportation. So you probably all know quantum teleportation, and probably all from the same source, which is the so-called the Star Trek series. So so again, what we're going to do here as an exercise is going from state characterizations to quantum circuits. What we just did now but a bit more complicated in the case of quantum teleportation. So the Star Trek principle of teleportation is that you want to go from a spaceship to a planet to visit without actually going there, but by being teleported there. So for that, people thought of a teleporter, and good old Scotty to send the captain and his crew from the ship to the planet, and they reappear on the planet and do whatever business they have to do there. So of course this is series, this is science fiction, but actually quantum mechanics tells you that this is possible. If you use, if you have few rules to follow, you have few rules to follow, but you can actually teleport things and people and whatever. So what teleporting means in that sense, but more to the point in physics sense point of view, well, first of all, and that's a big first of all, is that we need to destroy you, if you want to be teleported, in order to reconstruct you somewhere else, okay? And that is because, so whether it's you or a photon, which we're about to see, it's because I mentioned that during the first lecture, if you remember, is that quantum mechanics tells you that there's a strong theorem called the non-cloning theorem. And that is given by nature, given by physics. And it means that teleporting means teleporting. So it's teleporting you or a photon from one place to the other. But there cannot be a copy or a clone of you in one place or another. So that means we have to destroy the original copy in order to produce the other copy somewhere else. Okay, so that's the first step. So that means before you go into a teleporter, be aware of this, that you're going to be destroyed. So make sure this works first, okay? Then the second step is that, of course, we're not just going to destroy you, we have to entangle you with entangled particles themselves so that they will, in a way, conserve, or there will be a remaining of your memory of you, of what you are, of what makes you, or what we'll see, what makes the polarization state of a photon, which sounds more appropriate. And then the third, so that's that. So we have to entangle you in order to reproduce you somewhere else. And while we do this, we actually have to make some form of adjustments, once we teleported you, to make sure it is you. Okay? And so those three steps are basically the basic concept of teleportation. So if we manage to do this, then we should be able to do what Star Trek series was sort of imagining at the time. Of course, needless to say that when I say you, me, this is not impossible, but not far from it, because the calculation required, the technology, the engineering is just way, way, way beyond anything we can dream of at the moment. So we can't do that for us, sorry. But, or at least not for now. But we can do it for quantum particles, smaller particles, and we can do it for photons, and in fact, it has been done for photons. So let's go to that. So here is the real-life principle using qubits. So you want to teleport a qubit, so you have your qubit to be teleported, so say qubit, we will call it C. And we will, so that's the first, so first of all, you take your qubit to teleport. Then you create a source of entangled qubits between two, in this case we will use photons, so between two photons, A and B, like we just did right now. Then the third step is you make a so-called Bell measurement between the qubit to be teleported and one of the qubits, one of the photons of the entangled pairs, so say A and C. So qubit Bell measurements means a joint measurement, and a mixing of the teleported state with the entangled state of A and B. Then you transmit the result of your measurement to B. So this can be by classical mean. Just take the phone and say, this is what I found. So I found Bell measurements. So one of the 4 states of the Bell states, this is what I found. And then at the B location, which has now the other photons of the entangled pair, then B has to apply the right gate. And that's when I said the third step, remember, where we have to do something to make sure that it is U. But here we have to do something to make sure that we can actually convert and modify B so that now B becomes C. And effectively, what we did is we destroyed the original C through this joint measurement and made it reappear, or rather B became C, and now C has been teleported from this place to this place without actually going from here to there, because it stopped here and reappeared there. Okay? So that's the principle. And that we can do. We can't do it with people, but we can do it with photons. And in fact, it has been done, as I'll show you. So let's go through the mathematics and the state characterization to that. So first of all, we want to teleport qubit C. So any qubit can be written as a superposition of 0 and 1. So the wave function, psi of C, can be written as AOC plus B1C, right? Then we have an entangled pair of qubits A and B. So I chose the psi minus state between AB, which is 0, 1 minus 1, 0, with the obvious A and B, indices. So now if I consider, like we just did in the previous example, the tensor product of the 3 qubits, then I have the new wave function, phi CAB, which is going to be the tensor product of C and AB, right? And what I'm going to have is this state, which is A square root of 2, and then 0, 0, 1 minus 1, 0, 0, plus B over square root of 2, 1, 0, 1 minus 1, 1, 0. All I did was to take that and multiply it with this one to end up with this 4-term state. Okay? And now, so let's in fact, let's write this. I need, here we go. So C is to be teleported that's my initial qubit, so the general case is A0C plus B1C. Then I have A and B entangled. So I've got psi AB, which is going to be 1 square root of 2. And then I chose the state 0A, 1B minus 1A, 0B. Okay? So the 3 qubit system is the tensor product between these 3. So I call it phi CAB. CAB is going to be, so this times this, minus this times this. So A over square root of 2. Yes. So 0, 0C, 0A, 1B, minus 0C, 1A, 0B, plus the second term, so plus B, square root of 2, 1C, 0A, 1B, minus 1C, 1A, 0B. Right? And now what I can do is I can rewrite this in this form, where I would have 4 terms, you can see them here, where I separated the a new wave function, psi, so a new wave function of C and A, and separated the wave function of B, or the part of B. So, let me just check my notes to make sure. Okay. So if I do that, so I can, so for instance, let me check that. So we've got 0C, yeah. So I can rewrite this. So it's quite lengthy. So I will let you do that. So either you have 2 ways. So either you start from that, you start from that, and you're trying to remove. So you can, so for instance, remove OCOA and B. Okay, well, you can do that, and then make, for instance, you can add to this term, you can add OCOA 0B, which is not here, minus OCOA 1B. Okay, so this would be for this part, and you do the same for all of them. And then, so you just add and remove when it's missing, and then if you put those back together, so you would have, for each term, you would have, so 3 terms here, 3 here, 3 here, and 3 here. You can then put them together, and eventually you will end up with these 4 Bell states appearing. So this is the new psi CA. It's a wave function of C and A. We isolated it. We have it here, we have it here. We have it here as well, or here, or here. And then we've got B here, 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 or here, or here, or here, or here. Okay. And then eventually you will have these 4 terms with the 4 Bell states for CA. Or, which is maybe perhaps easier, although quite lengthy as well, is that you start from that and you take the 4 Bell states here and you just multiply them by those, and you will see that simplification eventually will lead back to this. Okay? So I'm not going to do it here because it's going to take some time. So I'll let you do that as an exercise. But it's just simple modification where you just take these states and sort of, shake it in calculations, so that at the end you have 1/2. So there would be 1/2 appearing because it would be twice square root of 2, 1 here and 1 with the entangled state from the Bell state. and then you'll have, so psi minus CA times minus A0B minus, B0B. That's the first one. You will get the second one, which is plus psi plus CA of minus A0B plus B. Oops, there has to be a 1 here, of course. Yeah. B plus 2 more terms, the psi minus, so the phi minus, and here we have A of 1B plus B of 0B, and the phi minus this time, no plus, sorry, which is going to be A1B minus B0B. Okay? So four terms. And so now in our protocol that we have here, so now we've got the state psi, so CAB, and now we make what I call earlier a Bell measurement between A and C. So a Bell measurement is basically trying to find out which of the 4 Bell states, so this one, let's put it in red, which of the 4 Bell states I'm going to find when I make a coincidence measurement at this place here, which is called the transmitting zone. Okay? Well, that's not a problem. I showed you earlier how we can do. We can just simply take the photons that come in, make some polarization measurement, and eventually being able to say, I measure this one, or this one, or this one, or this one. Okay? Of course, you measure one at a time. Say this one. You say, okay, this is the Bell state I measured. But then if you measure this Bell state for A and C, you haven't touched B, but what you did is you chose now, in a way, you projected how B is going to be. And B is going to be, so if you measure this one, say you measure this one, through a setup similar to this, to a setup similar to this, you measure this state. What that means that now, what you have is that B is in that state of A0B minus A0B minus B1B. So if you forget the minus, if you put the minus in factor, because it's just a phase, a global phase that we don't actually care very much, what you have is in fact this state. If you put the minus in factor, we can put it here, just to make sure. Oops. Can put it in front. Then we have created that state. So we have transformed B into C. So we have teleported C from one point, from this point here, this one, to this one, and where B became C. Okay? So, so that's it. This is the teleportation process. But now you may say, yeah, okay, but this is very well, but what about if you measured one of the other 3? Because if you measured one of the other 3, you can see that you don't end up with the same state here that you're supposed to. You don't end up with A0 plus B1, but you end up with A1 plus B0 or minus A0 plus B1 or A1 minus B0. Well, that's fine, because all you need to do is what I said is to apply the third step, which is on the teleported side, on B side, to apply a quantum gate, which is not going to measure anything. It's just going to modify the state so that accordingly to the measurement that has been done here, so that we end up with the right state. So in other words, if you measure, say, this state between C and A, so another entangled state, you get this one. Well, that's what I said. This part here, so usually we call the two protagonists Alice and Bob, you remember? So Alice will contact Bob and say, look, I measured this state. So Bob knows that then what he has to teleport is not exactly this. So he has to make a modification. So it's a simple gate, one qubit gate, on his B state so that he can transform this into the right one, which will be the teleported one. So here are the 4 transformations that he needs to do. If Alice, so if the one on the left-hand side, so if Alice measured the psi minus state, so the one I use is the easiest, Bob has to do nothing. You already get his teleported state. If she measures the psi plus state, then Bob has to make a rotation of 190 degrees around the z-axis, where z-axis has to be understood as the Bloch sphere, if you remember. And if he measures psi minus, then he has to do 190 degrees rotation around the x-axis. And if he measured psi plus, he has to, phi plus, sorry, he has to make a rotation of 190 degrees around the y-axis. Okay? So, you know, if Alice tells him this, he does nothing. This, he does something. This, he does something else. And this, he does yet another thing. And at the end, he will transform these 3, one of these 3, into this one, which is the teleported one that we wanted, without measuring it. He hasn't measured anything. It's just transform the state to make sure that he has the original state that was supposed to be teleported. And here we go. So now, let's have a look at the circuit associated to it. Well, here we go. The circuit is here. So we start with the 3 qubits. So size C, the one to be teleported. And then qubit A and qubit B, which are the ones that were entangled. So first of all, we entangled A and B. So we know now how to do that, right? We have to do Hadamard on one of them and Synod on the 2 of them. We just saw that previously. So Hadamard and Synod Gate. So at this stage here, we have the entangled state psi minus AB. Okay, that's the one that is here. I should have psi minus. Then next is I do a Synod gate between psi C, the C photon, and the A photon, if we talk about photons or qubits. And if I do that, then I create, so this is in a way the sort of artificial operation I did earlier. Well, I didn't do, but I let you do as an exercise. And here I created now the 4 Bell states between C and A, so psi minus, psi plus, phi minus, and phi plus. And at this, after, again, Hadamard, so which again is part of this transformation here, what I end up here is a 3 qubit state, which is the phi CAB. So this one. But this one with the 4 possibilities. Okay? And then I do a measurement, so the so-called Bell measurements. So C and A are measured. So here the measurements are done. And that's where Alice finds out whether she has this one, or this one, or this one, or or this one. She transmits, you can see, so this is something we haven't seen yet in the quantum circuit, but when you have a double bar here, it's a classical information. So she transmits to Bob her classical information, which is the result of what she obtained by doing the same experiment as I did earlier. And she says, oh, I find, say, psi minus. So now Bob knows what to do. He can apply or not an X or Z or Y, any operation, but a classical adjustment, classical in the sense that he knows from Alice which adjustment he has to do by applying one of the Pauli gates, single qubit gates, on photon or qubit B. But again, he, on the other hand, has not measured his photon, his qubit B. He hasn't measured it. Okay? He just transformed it reversibly with a quantum gate from the whatever state it was here to now the state to be teleported. So now B has become the original teleported state C. Okay? Excuse me. So this circuit here is exactly the quantum circuit representing this entire calculation here that we've been doing. So this was done experimentally. So the first experimental demonstration was done in 1997. So here's a snapshot of the publication. So this is from this publication. So you see here the same kind of diagram that I showed you, where you have Alice and Bob. You have, at the time, we talked about not an entangled source, but a so-called EPR source. So this is something we discussed, but not so much. But for some practical purposes, the same thing. So EPR stands for Einstein, Polonsky, and Rosen. So anyway, it's an entangled source of photons. So here, the photons is 1, and then you've got the two photons entangled together, created by this EPR source, this entangled source. So it's the same type of nonlinear crystal that I mentioned earlier. Then Alice makes that Bell measurement, where she jointly measures the qubit to be teleported and one of the qubit of the entangled pairs. And then Bob received the classical information of what he needs to do compared to what she obtained. So either nothing or some form of rotation. And basically transform his qubit here into the teleported qubit originally sent off. Okay? So here is the experimental setup. So here is the EPR source. So it's a nonlinear crystal. Here you've got Alice, and here you have Bob. So what we have is we have a strong laser UV pulse, again, going through the crystal, creating a first pair of entangled photons. So those are the two photons. So here they're called 2 and 3, but for us they were called A and B. Then there is a mirror that sends back the laser into that crystal in order to create a second pair, one being just tossed away, and the second one being the photon, the qubit to be teleported. And then what Alice does is that she recoups this initial state and one of the two photons from the entangled state, make a joint measurement, you can see here, so same type of thing that I did earlier, and make the so-called Bell measurement so that she ends up with one of these four states. And then classically, she tells Bob what she measured so that he, on his side, can analyze the state and eventually look at the right detector or apply the right transformation so that he ends up with the right state. Okay. So since then, we have progressed in terms of teleportation. Unfortunately, not for more than quantum states or polarization state of photons, or maybe quantum states of atoms or various spins and electrons and all. So at a single particle level, so not enough to teleport us for sure, and as I said, it won't happen for a long while, but nevertheless, this is a very important scheme that can be used for quantum technologies, and in particular for quantum communication, where you can teleport some information from one place to the other without actually taking the information from one place to the other. Okay? And this is used for quantum communication, for quantum computing protocols quite extensively, because it's a very, very powerful resources for quantum technologies. Right. So let's go back to quantum algorithm. So here I give you the program again. So clearly we will not be able to finish everything today, or at least not the part that I was planning on doing, but we'll see. So first, we will talk about classical algorithm very briefly for two reasons. One, because, well, there are probably thousands of different algorithms that exist out there. And secondly, because I'm not quite capable of going into the details of that. But we have to discuss where we come from in order to see where we're going from, and in particular on the first example of the Deutsche Algorithm. And then we will talk about families of quantum algorithm, and as I said at the beginning, that on the other hand, there are a lot less of them than there are classical algorithms. And there is still a lot of work to be done in order to come up with new algorithms, new quantum algorithms that can have useful applications. As I said, I will spend a bit of time on hybrid classical quantum algorithm, and in particular, I will focus on one experiment that was done yet again with photons to show you that this is a very good compromise between how can I use the resource of a classical algorithm, which are already extremely powerful tools for many applications and used every day, and the power of quantumness for quantum algorithms. So how can I use and put these two together in order to use the benefit from both for future algorithms? And then, as I said, there will be two examples, so the Deutsche algorithm that I will do, and then the Simon's algorithm, which led to Shor's algorithm, which will be done at some point by my colleague from INRIA. Right. So classical algorithm. So just a quick definition. Definition of an algorithm is a process or a set of rules to be followed in calculations, in computing, or other problem-solving operations. So simple example is a search database algorithm. So one of them, so a sequential search, also called a linear search. So I've got an array of how many? 9 or 10 numbers, and I want to find out number 33. So, okay, so here is an example of the algorithm. So it's a very linear process, and that's what you would do. And if you were to ask even a young kid would be able, you tell him there are 10 boxes, you have to find the green ball. Let's find out where it is. So what the kid is going to do is to open the boxes one by one and look for what color ball there is inside, and it will stop until he finds the green one. So here it's the same thing, but I want to know number 33. So here is a typical algorithm. So, you set the first register I to 1. Then you carry on. If I is bigger than n, then you go to step 7. That means you went through the entire, so n is the number of values, in this case 9. So if the register I is bigger than 9, then that means you're done, you haven't found anything. So you go to step 7. It says here, go to step 7. Fine, I go to step 7, and it says print element not found. I haven't found what you're looking for. Okay? If you're not in that case, then you go to step 3, which is that you go, you read what's at register I, and you read the value X. And if you found the value X that you were looking for, so in this case 33, then go to step 6. Step 6 says print element X, X found, so I found 33, and go at index I, so it can tell you where I found it, and go to step 8. 8 is exit, done. Right? If you haven't found it in your first occurrence, because you started at 1, well, then you need to go to the next occurrence. So you need to go from I to I plus 1. So from 1 to 2. And then you go to step 2, back again, and so on and so forth. And then eventually, you will either come out from step 7, which says not found, exit, out, or from step 6, which is element found at index I, exit, out. Okay, very simple. So it's a linear search where you search one by one. And if you remember, I didn't take that particular example, but I talked about search algorithm at the beginning, at my first lesson. And in particular, there is now the so-called Grover's algorithm, which is a quantum algorithm, which is a search algorithm, which scales up much faster than the linear classical one, as I gave you an example here. If you remember, what I mentioned is that in this particular case, for a search database, basically the time, the computational time that you need to resolve that problem is proportional to the number of elements you have to look at. Makes sense, right? If you have n elements, it takes time t to look for one element, then it will take you n times t to go through the entire chain of elements that you have to look through. But Grover's algorithm, by some clever way, can do the same, can obtain the same result in a square root of n time. So much, much faster. Okay? And that means that we can develop a quantum algorithm, we can develop quantum tools, so that we don't necessarily have to use those nice ones, but different ones. And that's what people are trying to do. As I said, different companies develop their own quantum software, different universities. It's still at this level. But there is a lot of work to be done, and there is still a lot of research to be done in this area. So, okay, so if we carry on, so there are different classes of classical algorithm, and I was expecting that, of course, but when I looked into what there is out there, sure enough, like I said, there are about thousands of them for any type of things you want to do. To even a search algorithm, there are many, many, many variations of them. From what I understand, you can group them in different sort of brands, which are given here, but they're just, from my understanding, they're just broad brands of what you have. But you kind of understand of, you know, if you do, if you use algorithm yourselves, to probably some of them make sense, like the brute force. So, for instance, I gave you an example of the brute force. You just don't think, you just open the first box, open the second box, open the third, and so on and so forth. There's also the greedy one, and then there's the divide and conquer, which sort of, in a way, you just split your problem into two, and then into two, and into two, and then it's sort of dichotomia kind of way of going down. There's also more clever one, more complicated one in a way, but clever one, like dynamic programming, backtracking, branch and bound, and so on and so forth. Okay. So there are, and again, this is just ... and I'm not an expert. This, I'm sure, is debatable by some people who say, yeah, but this is missing, or this shouldn't be here. I don't know. But what I do know, and I think everyone agrees on that, is that there are loads of them. And for instance, I found one sort of snapshot of what artificial intelligence, so the different categories that there is, just for artificial intelligence, a sort of machine learning classification. And you can see here that, well, you start from here, but then you have different branches, like planning, knowledge representation, perception, social intelligence, and then you go down to what is known as how you learn with artificial intelligence. Well, you have supervised learnings, you have unsupervised learning, you have reinforcement learning, and then for each of them you have different categories, and so on, so forth. Yet again, this is not my field at all, but I can see and I can believe that that's also one type of classification that, yet again, people probably argue that there are more because there are more. So, and all of this works very well. We know that we can use them. In fact, we use them every day. But like I said in my first lecture in the introduction, nevertheless, they are all using classical laws of physics. So they all have some limitations that cannot be beaten for some process, or at least not easily, that perhaps quantum circuits can do. Okay? And that's why like I said, there's a lot of work in quantum algorithms. So I'm talking about hardware. I've been talking about to produce these entangled states, there's these photons, these spins, and so on. But there's also a lot of work to be done in the algorithm and calculation part by trying to find better algorithm. So, quantum algorithms, there are also categories, but for that, there are a lot less of them, okay? There are basically 4 categories. Again, this can be, argued, but let's classify them in sort of these categories. The first one, which is a very powerful one, which is one that unfortunately we might not have time to do, at least during the lectures. We might touch them during the tutorials with the students, but we will probably not be able to do that during the lecture, is to use the quantum Fourier transform. And using the quantum Fourier transform, so the equivalent of the Fourier transform, but in using quantum laws of physics, then you can end up with most of the known algorithms that we know, that we've been using, that are useful, like the Deutsche Algorithm, the Simon algorithm, that will be, hopefully, that will be developed in lectures. Or, of course, the Shor's algorithm. The Shor's algorithm is basically, like I said in the first lecture, is a very powerful algorithm that can break any cryptographic system these days based on the so-called RSA system, which is basically to encrypt messages using a long chain of numbers. And if I send you a long chain of number, I ask you what are the prime numbers of this number, and this is extremely difficult to do with a classical computer. But Shor, with a quantum algorithm, came with an algorithm that can do that in a short time, or in a so-called polynomial time. You have also boson sampling problems, which are very much linked to photons, because photons are bosons. You have also another category, which we call the amplitude amplification category. So there are less algorithms, but there's still nevertheless a very powerful one, which is the Grover's algorithm, which is a search algorithm. So this we'll see also if we'll have time to touch that one. And then there is the family of so-called quantum walks. So the quantum walks is the equivalent of the random walk, but in the quantum world. And of course, the randomness in the quantum and what we mean by random walk has not the same meaning. And we have various algorithms. So here are some of them: element distinctness problem, the triangle finding problem, and so on and so forth. But the fact is that, of course, this is ... There are some others, but there aren't that many more of them. So as opposed to here, where there is no way I can put all the classes of algorithm in one slide, I can do it for quantum algorithm. So again, it shows you the interest, if you're interested in that, in trying to find out the next generation of quantum algorithm. So there's a fourth one that I wanted to spend a bit more time on, is the so-called a hybrid algorithm which mixes classical and quantum algorithm. And for that, there are, for the moment, the two most famous ones are the so-called QA01 and the VQE, standing for Quantum Approximate Optimization Algorithm and the Variational Quantum Eigensolver. So, yet again, I will not have the time to go through these algorithms. But I'll just give you, as I said, an example of, provide you with an example of an experimental implementation, what it looks like, and what's the principle of a variational quantum eigensolver, or VQE. So an experiment was done in 2014, and some others have been done since, where you have an optical chip here. So this is an optical chip. I remember I already showed you some of those, what they look like. And inside here, these lines here are light interferometers. Okay, so you have, if you remember, I showed you that, these beam splitters, these fibers and so on, where everything here, so these intersections here are beam splitters, okay? Except that everything is on a chip, as opposed to bulk elements like earlier on. And then in here, you can see these orange bars here with wires going off it. So these orange bars here are actually electrical wires, and those are phase shifters. They are basically heaters. It's just basically a small area where you will heat locally the optical chip. So why would you do that? Well, because if I heat locally this optical chip here, I'm going to change the optical phase within that particular interferometer, meaning that I will change the phase and therefore the state of the qubit, of the incoming photon qubit. So in a way, these are the gates that you can use. So these are the X, Y, and Z polygates. So rotation 1 qubit gates. And of course, all these splitters here, when you have them, these are a way of, if you remember, I showed you that, of creating spatial Hadamard gate between two input and two output. So in other words, you've got this entire photonic circuit with different gates, so Hadamard, single qubit gates, and you can transform and do pretty much here, as it's plugged in outside, you can change in real time what the gates you want to do. You want to do an X and then XZ and then maybe ZY and so on and so forth. So that's it. So what we have is we have two photons. They only take two photons here, two single photons coming in. So here we're talking about, as I said before, we're talking about spatial entanglement and polarization entanglement. So the state is 0, 0 to come in. So these photons go through all these optical chips. And then at the end, we've got 4 outputs and 4 detectors, where we can measure what the photon has been doing going through this entire circuit. What you cannot probably see here, but this one here in the middle, this part in the middle, by the way, is a Synod Gate. It's an optical Synod Gate. So this circuit here, this optical chip, only has one Synod Gate and many Hadamard, and, well, we can count them, but few Hadamard gates and few XYZ gates that are controllable from a classical computer, which has a optimization algorithm. And the variational quantum eigensolver, the idea is simply to run the simulation. So you go through the entire quantum part with operations, then you measure, you have a result, you send that back to your problem. So I'll come back to the problem that we're trying to solve with that. You don't really have the answer that is expected. So you modify your gates, your circuit, so that the next photons come in, give another result, but closer to the one that you were looking for. And then you do that again and again and again. And eventually, by some iteration, a certain number of iteration, where you adjusted every time your quantum circuit through a classical optimization algorithm, then you will end up with the result you wanted. So in this case, what they found is the ground state of the molecular energy of the helium hydrogen plus atom. Okay, so if you remember, again, at the first lecture, I mentioned that one thing that is actually very complicated in physics is that if I give you a given molecule, in physics, what's interesting to know this molecule is to know the energy states, the energy levels, the quantized energy levels of this molecule. And if you remember what I said is that we can do that for hydrogen, which is the simplest atom, the simplest molecule, it's a one-atom molecule, and we can do that analytically. Okay, in Quantum Mechanics 101, in any books, you can do that. It's already quite painful, but you can find the energy states of the hydrogen atom. As it is, as soon as you go to helium, then you're already in big trouble, and most likely you need a computer. This is not an analytical result. You need a computer to find the result. And then as soon as you go to a molecule, a proper one, so helium, hydrogen, so hydrogen plus, so basically what you have is helium and a proton that has lost its electron, then there is no way you can exactly find by any computers without some clever approximation, you can find the molecular energy levels. But this processor can do it using this so-called variational VQE method, quantum eigensolver, where you mix the quantumness and a standard classical optimization steps. So this is what it looks like. So here you've got the incoming photons from your SPDC source, spontaneous parametric down-converted source. Again, I promised you that this is very much in use for everywhere, and you can see why. Here you have the optical chip. Okay, so they call it the QPU, the quantum processing unit. And then you can see here all cables which are linked to the various phase shifters here. So those are these cables here, okay, and going to the CPU, the standard CPU, okay. So all these wires go to the computer, which gets the result. The computer gets the result from the detector part, which is here. Look at the state and compare it to what it wants to find out. Make adjustments, do the experiment again, make adjustment, experiment again, detection, adjustment, detect, and so on and so forth. And eventually what you have here is a graph of the energy level of the ground state, so the lowest energy state of this molecule, H plus helium. So the red lines are the predicted energy levels, and the dots are the experimental observation, the observed measurements, and the crosses are the theoretical ones, as a function of the optimization step. And you can see, so arriving at around 50 steps, so you've done through this whole process 50 times, then basically all your measurements are converging to a single state, which turns out to be the lowest energy state of your molecule, here. So after 50 optimization state. Without any surprise, and when you look at the first ones, well, they go everywhere. Well, of course, because well, at first you don't know, your initial step, can be anything and can give you the wrong result. So eventually there is wrong optimization and then better optimization until we get down to the bottom of it. And you can see that these dots have different colors. And you can see on the right-hand side that these colors go from 0 to 1. The different colors are a measurement of the tangling, which is a measurement of the entanglement power that is required to do that. And what you have to keep in mind, so those are all blue, so they are at the bottom level, because well, basically once we have reached the result, then the degree of entanglement required is less so. You can see it that way. And so this was done, by the way, so they found the ground state of helium hydrogen plus for a specific molecular separation of 90 picometers. And what they've done, which I haven't seen here, is they've done the same measurements for different separation and find basically the entire dependence of energy as a function of separation between the two molecules, which is again something that when you first open chemistry or physics books on molecular bonding, this is the first curve you see, where you see energy at the dependence of the separation between the two atoms, and that they managed to do that using this system, which is a mix of a quantum, so QPU, and a CPU, standard CPU, so a mix of quantum and classical algorithm. So I can't exactly go into the details of where the exact gain is, because it's quite it's not that simple. But to give you at least an intuition of it, is that so in order to do this, so we could have done that classically, but what we would have had to do in this part here, which we didn't do with the QPU, is that we basically had to store classically all the various possibilities and then eventually try them all to converge to the result. And that's where it would have taken a much longer time, is to try, again, like I said earlier, all the different possibilities by opening the boxes one by one, or here by going through all the various, this is a variational method, and to go through all the different possibilities and then eventually converge to one. But here, they didn't have to do all of this, because this entire part of exploring all the different parts and storing all the different possibilities were done in a quantum way, in a parallel way. So they didn't have to do that stage. So they took a much quicker time to do the same, to get the same result, by taking advantage of the quantumness of the superposition and entanglement and parallelism to reduce the otherwise classically consuming time required to do this type of calculation. Whereas the optimization algorithm in this case is a simple one and took a lot less time than exploring, again, like I said, all the different possibilities. And also, just to say that you could have said, okay, but this is nice, but what about if I used a fully quantum processor without this optimization stage? Well, you would have converged as well, but what's interesting is that in order to have the same result using a quantum chip like this, in fact, you can show that you would have needed 12 Synod gates, or around 10 to 12 Synod gates. So a lot more Synod gates. And Synod gates are not, if you remember I told you that, especially for photons, they are extremely, well, you can see one here. This is just one. So imagine a dozen of them for the same experiment. So we could do that, but in this particular instance, because the hardware is not so easy to manipulate to get the 12 Synod gates, then by using this hybrid method, they again make use of the benefits from both worlds, the classical and the quantum world. Anyway, so that was just to show you this. So there's a lot of work going on right now because, well, for the reason I said just right now, is that it's still, so there are two reasons. It's hard to have a quantum computer, a universal quantum computer. And also, well, not everything has to be quantumly sort of resolved. Some things can be done very nicely with a classical computer, hopefully. So that's why these methods are quite nice, because they combine the two and to converge to sort of simplification of some problems. And there's a lot of research going on right now on this. Right. So let's start. I will probably not be able to finish. But let's start with your very first quantum algorithm. So after this one, you will see for the first time that quantum algorithms are faster, better, and stronger, usually, than classical ones. So the Deutsche Algorithm, after David Deutsch, so it's quite old now, it's an old idea, but very smart idea, from 1985. And like I said, it's a very important step because it was the first, for the first time, it was the first algorithm that the quantum algorithm that could show that there is a gain in using quantum physics for that purpose. So on the other hand, it's a proof of concept, but it is not particularly useful. Or at least, I'm not quite sure what it can be useful for. But whatever, it's a proof of concept. It's to show, it's a proof of principle that, you know, quantum algorithms do exist, and they have, that was the first one, they do exist, and they have an interest, and they are better than classical ones, or some of them. So here's the problem that we want to solve. So let's assume that we have a binary function, f. So if it's a binary function, that means this binary function can go from 0, 1 to 0, 1. So if you think about it, there are only 4 possibilities for this function. Is either, so this function is a function that can do 4 things. It can either take the both inputs 0, 1 and map it to the output 0, right? So that means, so you have to imagine this function as a black box. So if I send a 0 inside this black box, then I end up with a 0. If I send a 1 into that black box, then I also again end up with a 0. That's the first case. The second case is the same, but now I'm mapping 0, 1 onto 1. So whatever comes in is 1 that comes out. The two others is that the inputs after the outputs, after the inputs are unchanged. So if I come with 0, I come out with 0. If I come in with 1, then I come out with 1. So that's this case. F doesn't change the inputs. And there is the fourth possibility, which is that F sort of swap or exchange the 2 results. So if input is 0, then it comes out 1. If input is 1, then it comes out 0. And that's it. Okay? There is no other way. And we can classify these 4 results into 2 categories. The first one is what we will call it the constant category, which is that whatever we choose, F0 will be equal to F1. Whether we come in with 0 or 1, F0 will be equal to F1. Okay? And the second class, for the other two, we will call it balanced. And that tells you that F0 will be different than F1. You see? 0 and 1 and 1 and 0. So in fact, these four can be categorized into two families of being constant or balanced. And the question is, so the question you want to answer is you want to find out whether the function is constant or balanced in the minimum number of steps. I told you, not very useful, but nevertheless. So, okay, so how would a classical computer do? It would do it in two steps, two evaluations. So first, it says, okay, if f equals 0, then we have two possibilities. If f equals 1, that means f1 equals f0, then we print constant. Otherwise, we print balance. And if f of 1 equals 1, then we print balance. Otherwise, we print constant. Right? So we basically need to look at f0 and f1 and just compare them. That's it. But we need to measure both. We need to measure f0. We need to measure f1. So we need two evaluations in order to answer that problem. But with Deutsche's algorithm, we will see that we only need one instance. So let's see how we will do that. So quantumly, one evaluation is needed if you use this algorithm, which is the Deutsche algorithm. So let's put that into, let's cut it into different parts. So for Deutsche algorithm, you need two qubits. You need Q0 and Q1. You need to initialize them first. So in this case, the first one has to be 0 and the second one has to be 1. Then you need to apply a Hadamard gate on each of them. Then you need to do a unitary transformation which represents your function. So I'll come back to that later. Then you take the first qubit, you apply another Hadamard gate, and you measure. And by doing so, instantly, as we will see, you will know what the result is, whether it's constant and balanced, by doing this measurement. And in fact, you don't even need to make a measurement on qubit 1, because this will give you in one instance. So you can see there's not a second measurement, because you don't actually need the other one. But in one instance, by one measurement, depending on the state you will find, so 0 or 1, by construction of this quantum circuit, you will know whether it's constant and balanced. So in one evaluation, one iteration, you have the answer that took you 2 iterations in a classical equivalent. Okay? So let's just start, and we'll carry on next time. So at each step, like we did before, we will look at the quantum state that we have. So the first one will be the initial state, psi 0. And the second one, psi 1, after the two Hadamard gates. Then the third one, psi 2, after this unitary operation that represents the function f. Then phi 3, after the Hadamard gate. So in each step, so we'll have psi 0, so 0, 1. Then psi 1 after the two Hadamard gates, so we'll come back to that. So two Hadamard gates will transform 0 and 1 into plus minus. So we'll have the 2 qubit state that looks like this, a bit like what we did earlier on. Then we apply to this 2 qubit state, we apply this unitary operation that I'm about to describe. So this has to be unitary, of course, and we talked about this. So there has to be a quantum gate, And unitary means there has to be reversible. So in other words, there has to be something that will not, of course, measure by any mean the state, but just transform it. And that's the function that we want to look for. But it's something that we do not have to know. Okay, we do not have to know, in fact, what's inside that box. All we need to know is that this, and we'll see what can represent any transformation f to uf, is that this is a unitary transformation that represents the f function. So sometimes people talk about some form of oracle, where you interrogate the oracle. That's all you can do in order to know whether what you say is the right answer or not. So you can see it as a... So sometimes people talk about the quantum oracle. And so the next steps will be first to define this unitary function, unitary gate, sorry, 2-qubit gates. Then we will look into what we have, so the psi2 state after that unitary gate, so something that looks like this, where we have, without breaking any news, we will use so the unitary transformation here will be XOR function between the two qubits, so XOR, addition between the two qubits. And then the next step will be the Hadamard transformation and the measurement. And for that, we will split into two cases. So if f is constant, we will see what result we get. Or if f is balanced, we will see what result we get. But what I can tell you already is that at the end, you get, so you measure this qubit, which is the top one, and you have a second qubit, so you have a tensor product between this one and this one. This one is in some form of superposition state, but actually you don't care about this one. You can just throw away this one, because you're going to measure this one. And you can see here that if f is balanced, you will measure a minus state here. Oops. So a minus 45-degree angle, for instance. Whereas for the constant case, what you will find is that the measurement will give you plus. And something else here that you don't actually care about. So you can see that by one measurement, you will either find plus or minus corresponding to the balance or the constant case. So in one instance, you're able to tell what the function is, whether it's balanced or constant. And that's the whole principle of Deutsche Algorithm. And with that, I will stop here. We will go to that probably next week, like I said. So probably next week, it will be me again. But if it's not, there will be someone. There will be a lecture for sure. Same time, 10:10 next week. And with that, I thank you very much, and see you next week.